Alright, in part 2 of this video series, we're looking at some of the pre-calculus style topics, but with an IB twist. And this one deals with polynomial functions, their zeros and their equations, and it also deals with function transformations. And there's some non-routine elegance that goes on with solving this particular beast down at the bottom. As before, I pointed out the mark scheme, and we can kind of observe that the first part of this problem is going to involve just a little bit more meat than the second one, but they're both sort of equally balanced in terms of their sort of involvement in thinking and conceptual understanding. What I need to do is first recognize that we have a cubic function, and the a value of that cubic function, that is, the coefficient on x cubed, is 1. Now, I did my work without, or pretending not to know that. I was just sort of kind of more generalizing this approach, but I want to show you what I did and realize that what I did is a little bit less efficient than is necessary for this problem, but what I'm going to show you is a little bit more generalizable. First, I identify all of the major characteristics that are known facts. Anything else that I notice on this graph is inference, but these points that are labeled are in fact true as solutions to this particular equation. So when I write this, I write actually the function is some constant times the product of all of the roots, the linear factors. If you multiply 3 linear factors together, you get a cubic function in this form every single time. It's just the difference is where the linear factors are. These linear factors are based on the zeros or roots. So if x equals 2, x minus 2 is 0. 0 times all this other stuff is 0, so we have an x-intercept. So by knowing the x-intercept, we work backwards to find a linear factor. 3 linear factors multiplied together come to produce a cubic polynomial as shown. Now, this should be enough information to answer the question about what a, b, and c are, especially since 2 right here is automatically the y-intercept. When I put in 0 for x, I'm going to get 2 times a, which means a is 1. So I didn't need to do that. I could have gotten lucky and gotten the right answer without this verification, but there might be an instance where the y-intercept and this value as a product of your linear factors, where these don't match. And if that happens, we can actually evaluate for a by using the y-intercept when x equals 0, put in 0 for all the x's, there's a constant. 2 times a has to be 2, which means a equals 1, and here, this without the a value is my function equation, as shown. Now, just to make sure I'm doing everything, the question asked me to find the values of a, b, and c, so I explicitly state the values of a, b, and c after stating the function that I found. I think I've adequately justified this work, but of course I can go to Desmos later and make sure I get the same graph. Before I do that, I'd like to take a look at the rest of the story. The function already given is here, and that's what I found in the first part of the exercise. Now I have a transformation. G of x is defined as 3 times f of x minus 2. So everywhere I see an x, I resubstitute with x minus 2. And then I remember what I learned about function transformations and their universality. Remember that subtracting 2 from x actually has the effect of shifting the graph 2 to the right, and multiplying f of x by 3 has the effect of vertically stretching the graph. That is 3 times all the y values that used to come out of the function. So g of x is going to look like a cubic polynomial, it's just going to behave a little differently, shifted to the right and vertically stretched out. What we were asked to do is to state the coordinates of the points the graph of G intercepts the x-axis. I think intersects the x-axis is a better word, but anyway, since the function is shifted to the right too, I could ascertain that all of these x-intercepts are going to be shifted to the right too. So negative 1 will shift over to 1. 1 will shift over to 3, and 2 will shift over to 4. So, the coordinates of the points where the graph intercepts the x-axis, those points are going to be 1, 0, 3, 0, and 4, 0. That is from the shift to the right 2. The next thing I have to do is find the y-intercept. And this is probably the most challenging piece, because some people might think that to find the y-intercept, I need to simplify this beast. Find the whole polynomial. But really, I'm just looking for the constant that's at the end. Now, these numbers in here are going to affect the constant, so it's not going to be 2. More evidence to support that it's not going to be 2 is this graph is shifting 2 to the right. So the y-intercept is going to be some negative number down here somewhere. So to not have to FOIL this out and to still get the result is going to be the challenge for this particular task. So what I'm going to do is I'm going to substitute 0 for x right here. 0 for x, put 0 everywhere I see an x, and I end up with 3 times negative 12, which ends up being negative 36. So this is actually an easier way to number crunch. You don't have to FOIL this this whole beast out. You don't have to FOIL that all out. You just put in 0 for x without doing that, and you find it's just a numerical exercise. 0, negative 36 represents the y-intercept of the new transformed graph. Again, none of this is complete without a look at the old Desmo. Once I see the graph, and notice, by the way, what I entered. I entered the cubic function that was given there that I found in part A, and then all I had to do, if I use f of x notation, is write new equation y equals 3f of x minus 2. So again, I didn't even have to find algebraically what my new function is going to be for g of x. I just had to take the original function and let Desmos apply the transformations. So the beauty part is we now have 1, 0, 3, 0, and 4, 0 to verify my x-intercepts, and I also have 0, negative 36 to verify my y-intercept. So there you have it. Thanks for watching.